All right, so this is, I didn't write down what the number is, but this is, I think, A3. Yeah, so this is A3. Right, so A3, calculate the frequency range of UVA radiation. So that's from 315 nanometers to 400 nanometers. So the equation that we use in this case, right, is the E is equal to HC over lambda. And so if we first calculate the one for 315, the frequency range, not the energy range, right? The frequency range, right, would be nu is equal to C over lambda. And so C is the speed of light. So if we do 2.9979 times 10 to the negative 30, nope, I'm thinking of H, times 10 to the 8 meters per second divided by, right, we have the two wavelengths, so we have 315 nanometers, and so we have to convert that into meters, so that's 1 times 10 to the 9th meters per, or negative 9th meters per nanometer, right? So nanometers cancel, meters cancel, we end up with per second. What we get is 2.9979 times 10 to the 8th divided by 315 times 10 to the negative 9. Comes out to 9.52 times 10 to the 14th per second, right? Which is what I have here, I think, 9.52. Yep, exactly. So we can do then the same thing for the other equation, right? So that would just simply be, wavelength. So that would be 2.9979 times 10 to the 8th meters per second over 400 nanometers times 1 times 10 to the 9th meters per nanometer. Nanometers cancel, meters cancel. What we get is 2.9979 times 10 to the 8th divided by 400 times 10 to the negative 9th. Forgot the negative right here, writing it out. Comes out to 7.50. No, 7.49 times 10 to the 14th per second, right? Which I think I'd have here, right? Yeah, 7.49, right? So that's the range that you're going in those cases. So part B, calculate the energy of a photon of these wavelengths in joules. So all we have to do for that, right? So the equation is, HC over, wavelength, or we can also just simply use the frequencies that we just calculated, right? That would just simply be H times nu. And so in both of these cases, right, H is 6.626 times 10 to the negative 34 joule seconds. So if we just simply use, these values times 9.52 times 10 to the 14th per second, right, what we get is seconds cancel, so we only end up with joules. So, right, the first energy then is 6.626 times 10 to the negative 34 times 0.52 times 10 to the 14th. Comes out to being 6.31 times 10 to the negative 19 joules, right? Which is basically what I have right here. And so then the second energy, if we just simply plug in, right, these values, what we get is 7.49. 4.96 times 10 to the negative 19 joules, which is what I have right there. Right, so those are the values that you would need in those cases. So part C, UVA penetrates more deeply into the skin, but UVB more readily causes sunburn. These UVB photons have a frequency of about 1 times 10 to the negative, or 1 times 10 to the 15th hertz. How much more energy do they carry? So, right, what we have to do in these cases is first convert this into energy, right? And so to do that, we go E is equal to H nu. And so we have 6.626 times 10 to the negative 34 joule seconds times 9.52 times 10 to the 14th per second. Excuse me. Oh, wait, no, I was looking at the wrong numbers. Sorry. Times 1.0 times 10 to the 15th per second. And so that energy comes out to being 6.626 times 10 to the negative 34 times 1 times 10 to the 15th comes out to 6.626 times 10 to the negative 19 joules, right? So that's the low end of the UVB radiation, right? Has that much energy. And so if we're, trying to think about how much more energy they carry, we just simply have to subtract the two, right? So the difference in energy in this case, right, E of UVB minus E of UVA, is going to be 6.626 times 10 to the negative 19 joules minus 6.31 times 10 to the negative 19 joules, which comes out to 6.31 times 10 to the negative 19 joules, 3.16, right? Which is, 3.3. Close enough. 3.16 times 10 to the negative 20 joules. Right, so that's the energy difference there. Because again, you should be subtracting the energy values in these cases from each other. All right. Part D, a red laser pointer emits light with a wavelength of 700 nanometers. A fancy green laser pointer emits light with a wavelength of 500 nanometers. Which emits more energy per photon? Right? And so now, again, you just do the same equation, the same application that we've been doing for a lot of the other problems that I've worked through today already. So the energy is equal to HC over lambda. Right? And so HC, I'm not going to work through the rest of this just because it's getting very repetitive and there's been a lot of other questions related to things, but you plug it in there, right? You have lambda. Make sure that you're converting the nanometers into meters, and you should be able to then see the get the values, right? H is in joule seconds, C is in meters per second, and so lambda has to then be in meters so that the meters cancel out in those cases. All right.